Hello, friends. Welcome back to Accelerate AI Careers. Today, we are going to continue the next chapter in our NLP Fundamentals playlist, wherein we'll be covering word embeddings. Now, why I have not spoken about word embeddings for so long? Because I was still waiting for you to get acquainted and grasp the concepts of how we convert word to vectors. Now, I feel like we have done some techniques such as one hot encoding, bag of words, TF-IDF, and we are now ready to cover these concepts as well. So today we will be highlighting what actually word embedding is. What are the different techniques used in word embeddings? So mention in the comments here if you like the series and if there are some important topics you would like me to prioritize first. So let's get going. Now you must be wondering, what are word embeddings? The Wikipedia definition of word embedding says that in natural language processing, it's the term which is used for representation of words for text analysis, typically in the form of a real valued vector that encodes the meaning of the entire words, such that the words which are very closer in vector space also are expected to be similar in meaning. So the keyword here is similar in meaning. What does it mean? Say suppose two words have very similar meanings, for example, hot and warm. Then they would be very close to each other in vector space. Now, assuming it's a two-dimensional space, I can explain it to you with an example as shown here. For example, we have four words: curious, happy, excited, and angry. So these are four feelings which a person experiences, right? And we all know that curious, happy, excited, these are kind of positive feelings and they are in the similar zone or same kind of feelings. And then they should be close together in the vector space because they have kind of similar meanings. Whereas angry, that's a different emotion, which is kind of an opposite emotion to happy, excited, or curious, and should be in a different vector space. And that's how it is shown by the 2D diagram here. And we can convert word to vectors by different ways. Suppose we are converting it using PCA, Principal Component Analysis, and that's how we have depicted them here for the ease of understanding in a 2D space. They need not be in a 2D space. So I hope you understand what actually word embedding is. What is the meaning of having them closer in vector space and similar in meaning. Now, it's not like this is the first time you are starting with word embeddings. We have already covered three different kinds of word embeddings, which are one hot encoding, bag of words, and TF-IDF. But let me explain how word embeddings are structured. So there are two kinds of embeddings. One is that is based out of count or frequency, which we have studied so far, like one hot encoding, bag of words, TF-IDF. They all have their advantages and disadvantages. Some of the disadvantages are they are sparse in the vectors. There are a lot of zeros. They do not capture the semantic meaning. So all these things need to be handled. Then there are other kind of word embeddings that came into picture with deep learning. And these include deep learning trained models, which are more accurate, which perform really exceptionally well, and they capture two things really well. One thing is that they are accurate representation of the words that are real valued representation vectors. And the second thing they capture really well is semantic meaning or the essence of the words. So basically, two words which are similar in the context are closer when compared to the one which is opposite to the meaning. So that's how deep learning trained models came into picture. And what is this deep learning trained model called? It's called Word2Vec. I'm sure you have heard about it somewhere. So I'll go deeper into the details, how we train Word2Vec, how we can use Google pre-trained models for Word2Vec. We will delve deeper into it, but on a higher level, Word2Vec can be of two different types. It could be CBOR, which is continuous bag of words, or it could be a skipgram. We'll look into each of these in the following video. Let me know, did you get a proper understanding of all these techniques and which one is your favorite one in the comments if you have used them ever. Now friends, what does Word2Vec technique means? So let's refer to its Wikipedia definition and I'll explain you how that technique works. In future, we'll also look into how to train such a model. These models are big models like 1.5 gigabytes. And this Word2Vec technique was introduced by Google in 2013. This is a technique which is basically used to generate vectors out of your words, or basically vector representation of words. And as I told, these are deep learning method of generating word embeddings and not the count or frequency method. This technique basically uses a neural network model. Remember that it uses a neural network model which is trained to learn word associations and relationships. That's a key word. It learns semantic relationships and associations from a large corpus of text, and it generates vectors. So these vectors capture information about the meaning of the word based on the surrounding word or context. Once a trained model is deployed, such a model can detect synonymous words or suggest additional words for a partial sentence to complete that sentence. So, Word2Vec technique is broadly broken down into two methods. One is continuous bag of words or CBOW, and the other is skipgram. We will look into each of these in detail, and I'll explain you the architecture, the in-depth view and usage of these techniques, as well as their advantages and disadvantages. And we'll do some practical implementations using these techniques also. So stick with me to the end of the video. Now let's delve deeper into Word2Vec embeddings. So first of all, I would like to mention one key word here, feature representation. So any of the Word2Vec embedding techniques generates feature representations for you. That is a vector that is based on certain kind of features. Let me explain it using an example here. Say suppose we have this vocabulary. Vocabulary means your unique set of words in your corpus, okay? So your vocabulary comprises of only these 6 words: a boy, girl, king, queen, apple, and orange. And you will make feature representation of these words, natural language words. That is, you would generate vectors based on certain features about these. So let's look into the details, what features they could be. Now say suppose one of the features is gender, another of the feature is royal, the third feature could be fruit, the fourth feature could be say age, 6 could be food, and say suppose we have 300 of such features, 300 dimensions. And each word, say boy, will be represented in the form of these 300 dimensional features. Similar to that, a girl will be represented in these 300 features. So you will be essentially creating a vector based on this relationship of this word boy with these features like gender, royal, fruit, age, and there would be certain number that would be placed in front of each feature for that particular word. And that's how you create that unique vector representing each word. Now, this is just for the sake of explaining with an example. I'm showing 300 dimensions and this here. But in reality, this is a very big vector and it is not usually possible to see all the features. For example, when Google released Word2Vec, they actually used the feature size of 3 billion parameters. So it is impossible to see all those parameters coming from the news feed, which Google is using. But they use essentially 3 billion features to make the feature presentation for each word. So we will look into that. We'll be using that real time, that model as well. But for the time being, let's work on getting these vectors out of these features. Now let's look at the vector values here. So I'm just filling out values here just for the sake of explaining in the example, but usually these values are filled out by a trained Word2Vec model, a neural network model, which is trained on a very large corpus. For the sake of explaining here, I'm explaining using certain values. So say suppose we are filling out the vector representation, feature representation for boy. So now boy, for example, for gender, it takes the value -1. Then the girl will take the value as 1 for gender. Same way for king, the value would be somewhat -0.92, and for queen, it would be just the opposite, 0.95. Apple and orange do not have relation to gender, so their value will be very close to 0. Now for royal, a boy and girl have very little relationship with the feature royal, so the value will be very close to 0. Whereas the values for king and queen will be close to 1 because they have very high correlation with the feature royal. Apple and orange do not have any correlation with the word royal, so it would be closer to 0. Now for the word fruit, boy, girl, king, queen all will have around 0, whereas apple and orange are fruits, so they would be close to 1. Now for the feature age, boy and girl might not have that direct correlation, so value will be close to 0. While we usually say this king is old or this king is young, this queen is old or this queen is young, so they have a correlation with this feature, so their value will be greater than 0.5. For apple and orange, they might have a very high correlation with this feature age. For example, an apple was on the shelf for 10 days. An orange was on the shelf for 5 days. So it represents their age. So it might have direct correlation. Hence, the value is closer to 1. For food, boy, girl, king, queen might not have direct correlation because food is not related to any of these. Whereas apple and orange are food items, so their values will be correlated and will be around 1, as you can see here. So that's how we devise the feature representation here, but it is not done manually as there are not 5 or 10 features involved. There are 3 billion, 4 billion features involved, and it's usually done using the neural network model trained on a very large corpus. Now, this Word2Vec feature representation has lots of advantages. One of those advantages has also been mentioned in Google's research paper, which is like you can obtain one feature representation by using other feature representations. For example, here, if you subtract the boy feature representation vector from king and then add queen feature representation vector, you are bound to get girl feature representation. Essentially, king minus boy plus queen, the feature representation, will lead to girl feature representation vector. So you can also check that by making your own calculations once you are using the model in real time. And we'll look at other applications as well, but this is one of those applications. Now let us look at another concept, which is cosine similarity. Why we are discussing it? Because these vectors essentially, what do they represent? These vectors represent some feature representation for each word you have in your text, in your context. Now each word, how much it is similar to another word or how much it is farther from another word is calculated by distance, and that distance is equivalent to 1 minus cosine similarity. Now what is cosine similarity? So, for example, we have two words, boy and king here in our two-dimensional vector space representation. And say suppose the angle between these two words is 30 degrees. So here cosine similarity is given by cos. So cos of 30 degrees would be root 3 by 2, which comes out to 0.866. So essentially the distance between these two words, like how far or how near they are in terms of meaning within the particular context, would be 1 minus cos of 30 degree, which is 1 minus 0.866, which comes out to 0.1339. Now, when you essentially say, what is this 0.1339? That means that a boy and king, two words are quite similar, and the distance between them is very less, which is 0.13. Now, let us look at another example. Say, suppose the two vectors in the same two-dimensional vector space are 90 degrees apart, that is on different axes. So in that case, the cosine similarity would be cos of 90 degree, which would be 0. And distance would be 1 minus cosine similarity, which will come out to be 1 minus 0, essentially 1. So the distance between two vectors is 1 and they're poles apart. Now let us look at another example. When the angle between the two vectors on the same two-dimensional vector space is 0 degrees, what happens then? In that case, the cosine similarity would be cos of 0, which is 1, and the distance would be 1 minus cosine similarity, which would be 1 minus 1, that is 0. So essentially the distance between the two vectors would be 0, that is they are not apart at all. They are quite similar. Now this particular use case has several examples. One of such examples is recommendation engines. So let me explain it to you with an example. Now in recommendation engines, say suppose you have a feature representation which comprises of features such as action, comedy, romantic, fiction, superheroes, and so on. So these are all your features which formulate your feature representation for your certain entities. And your entities could be your movies such as Captain America, Avengers, Hulk, Iron Man, and so on. So all these movies are kind of the same genre, as you can recognize, and they would be very close in the vector space like you can see. So essentially this is also one of the examples or use cases of feature representation and cosine similarity, wherein you calculate the distance between one entity to another entity, that is their feature representations, and if they are closer, you make the recommendation to the user based on, say, like you watched Avengers just now, and this movie like Captain America is of the same genre and you have not watched it yet, it might be of your liking. So your recommendation engines essentially make use of these three concepts: feature representation, cosine similarity, and distance between these vectors. Remember that action, comedy, romantic, all these are your features, whereas your entities are your movies. Okay. So what next? Right now we assume certain values for each feature of each vector, but we didn't calculate it actually. So in the coming video, we will see how these values are actually computed by looking at the larger corpus and using neural networks. And we'll also use them in a practical project implementation. If you are interested to learning more about it and getting the latest update on the next video, subscribe to my channel now, like and share the video with your network if you like it. Thank you.